Today I talk about how to obtain the optimal observation error covariance matrix. I use the notation R as usually used, as is usually used. This slide shows the result of my today's talk. Optimal R should satisfy this equation. It means the R should be a linear combination of two terms. The first one is the ensemble mean of innovation squared. The second term is the prior covariance matrix. These two terms has coefficients 1 minus lambda and lambda. The lambda means the weight for prior covariance matrix. The 1 minus lambda is the weight for the ensemble mean of innovation. So in general, covariance matrices are known to affect the estimate of the data assimilation. I showed the two ways of data assimilation formulation. One for the sequential ones, the second one is the variational data assimilation formulation. In both formulations, covariance matrices appears as the initial state or background state, and the model random error and observation error. The B, Q, and R also appear in the cost function as B inverse, Q inverse, and R inverse. So in this presentation, I focus on the RT matrix. RT is the observation error. Here I assume R includes the error due to the instrumentation accuracy and also the model representation error. So this shows our review for former studies for estimating covariance matrices. The former studies are roughly classified into four. The first one is minimizing innovation to obtain the optimal covariance matrix. The second one is the maximum likelihood. The third one is the Bayesian estimation. The fourth one is the method called the covariance matching. Among those four methods, maximum likelihood or variance based on the maximum likelihood is widely used, I think. In the maximum likelihood estimation, many studies assume adopt the assumption of Gaussian distribution of state. And some studies do not use the Gaussian assumption of state. Here, I show the method belongs to the third group, Bayesian estimation. In the Bayesian estimation, there are two ways. One is use the assumption of Gaussian distribution of state, and the other is without the assumption of Gaussian distribution of state. Here, the method I propose here is this one, Bayesian estimation of covariance matrix without assumption of Gaussian distribution of state. The tool I use here is the ensemble mean of likelihood and the prior distribution. And as is written, the ensemble mean is used in this method. So the method I propose here is applicable to the ensemble-based data assimilation method, like ensemble common filter or particle filter. So first, I define the observation error covariance matrix on R1 to R capital T. The subscript T means the observation time step. So R1 means the observation error covariance matrix at time step 1, observation time step 1. And R capital T means the observation error covariance matrix as observation time, final observation time step. In the next line, I present the likelihood of R covariance matrix. The first line shows the ensemble approximation of log likelihood. Here I use the small n, means the each ensemble member. This the summand p py given x and r means the likelihood of ensemble member n. And then take the average, means the ensemble mean of likelihood of each member. Then take a logarithm, then take the summation to compose the likelihood function of the whole observation, all observations. And this likelihood function is explicitly written like this by assuming the observation error is a Gaussian distribution. Here, these logarithm and the determinant and exponential function comes from the assumption of the observation, a Gaussian observation error. Next, I assume here the LT as the summand of these in the second line. So the likelihood of R1 to R capital T is represented by the sum of the LT, the likelihood of each time step. So in the maximum likelihood estimation, our purpose is to find the R1 to R capital T that maximize this value. This value means the ensemble approximation of log likelihood. So I showed the estimation design. I showed the likelihood function in the previous slide, but this formulation cannot be directly used for estimation of R. I'll explain the reason here. The LT, the likelihood function at time step t, is written like this. And the LT is a function of R1 to RT. And then the R1 to RT can decompose into R1 to T minus 1 and the final time step RT. The reason I would decompose the set of R1 to T into two terms means the reason is that in the right-hand side, RT appears here and here as it is, but the dependence of R1 to T minus 1 affect the right-hand side implicitly through the predicted ensemble or forecast ensembles like this. So RT appears explicitly in the right-hand side. So I make a decision to I make an estimation design that is use LT for estimating RT only. But this likelihood function means the LT is a function, also a function of R1 to RT minus T minus 1. But here I assume the R1 to RT minus 1 are already fixed through the formal log likelihood L1 to LT minus 1. So I use LT. LT means the likelihood function used in the Tth observation is used to just estimate RT. R1 to RT minus 1 were already fixed using the formal observation Y1 to YT minus 1. So this is the design I adopt here. Of course, there shows two bad news. The one is that I estimate RT every time step. So the estimate RT may vary significantly between different time steps. And the other one is that time constant R cannot be estimated within this framework because the RT is estimated every time step of the observation. So here, in the following, I show three types of experiments. Depends on the structure of RT. Case one is RT is assumed to be a scalar. The alpha t is a scalar variable that should be estimated times fixed covariance matrix. So case 1 just estimates the scalar coefficient. In case 2, I assume the RT is a diagonal. R1, so the parameters are R1 to Rm. Rm is the dimension of R of each time step. And then in case 3, general RT, I'm going to estimate. General RT means the R has no some mathematical structure. So I showed the data and the model used in the estimation experiment. These are the sea surface observation for 10 years, the longitude versus time for 1992 to 2002. And this is the output of the coupled model by Ziviak and Kane in the Equatorial Pacific. The color shows the sea level anomalies. This is just the model output. First, I show the result by the maximum likelihood estimate of RT. In case 1, I assume the RT is the a scalar times some fixed covariance. And this shows the estimated R as a function of time, 10 years. The vertical axis shows the estimated variance. It shows they estimate highly fluctuate like this. In the case 2, R becomes like this. Case 2 means that R is assumed to be diagonal. So one question is that it is reasonable that RT varies significantly with the time like this. In my position, it is not, and I developed another method. Here I use the likelihood function. Then the estimate varies significantly with time. I introduce the prior distribution to estimate to carry out the Bayesian distribution. The Bayesian distribution maximizes the posterior distribution using the product of the likelihood function and the prior distribution. The prior distribution, I adopt the Wishart distribution. It is the standard distribution for the covariance matrix. And the Wishart distribution also has additional parameters. And the additional parameters can also some degrees of freedom, but can objectively estimate by maximizing the marginal likelihood. The marginal likelihood is the likelihood function of the parameter for prior distribution. It is obtained by marginalizing out the R, like this. In this formulation, the ensemble means ensemble approximation of likelihood is written like this, and the Wishart distribution appeared here. And in this formulation, the integral has an exact solution that becomes like this. So I use this marginal likelihood to estimate the optimal parameter for the prior distribution of RT. Here I show the algorithm. The optimality condition means the posterior distribution. I take a derivative of the posterior distribution of RT and put equal to 0. This equation is equivalent like this. The RT should be the linear combination of the ensemble likelihood and the prior distribution. And the Z is defined here. The Z is the function of R. So it means the R should be a function of R plus lambda S. So the R is a function of R. Then I use this relation by putting some initial guess of RT 0 and to evaluate the right-hand side to compute the left-hand side. And the obtained left-hand side value, I define the left-hand side as R1, and then repeat the same procedure by substituting R1 to RZ in the right-hand side obtained R. So using this algorithm, the maximal likelihood estimate becomes like the Bayesian estimation like this. The estimates becomes much more smooth and stable in time. And this shows the one example, the Equatorial Pacific. These are the temporal variation of variance for 10 years and the spatial pattern of variance elements and the covariance elements. The covariance elements have the zonally elongated pattern. So I skipped here. Here the summary. Here I show the algorithm for Bayesian estimation of observation error covariance metrics. It is based on the optimatic condition of R, and I found the closed form of R. And using the closed form, I construct an algorithm. The prior distribution also has the additional parameter, but the parameter also objectively estimate by the maximizing the likelihood. And I showed the application of coupled model. So that's it.
Yes, many thanks.